Hello. The principle of inclusion-exclusion, affectionately known as PIE, right? PIE. This is a result about counting the size of a union, right? Counting the number of elements in a union of two sets. So you have two finite sets, A and B, and we want to say how big is our union. So we're looking at in a Venn diagram, we would be looking at this region. What is A union B, right? It's everything in A with everything in B. And when you take a union of two sets, you make one big set that dump all of the elements into one big bucket, right? So it kind of makes sense that you would say that the union should be the sum of the size of the union should be the sum of the sizes of each of those sets. Except there's an issue here. What's the issue? The issue is if you think about how many times, say in this Venn diagram, have we counted each region? Well, A included all the elements here and included all the elements here. B included all the elements here and all the elements here. So what happens if you just do this, it would count A intersect B. Anything in there got double counted, right? It would overcount the elements of A intersect B. So that's why what do? We then subtract them off, right? To get rid of one of those dots in A intersect B. And oops, I just realized I have the wrong side. That is not A union B, A intersect B. There we go. The union is the whole big red region. The intersection is that overlap. So that's what we have, right? We have you subtract off A intersect B, and then it tells you the size of the union, right? So let's look at this in an example, right? In a really specific example. Let's find how many numbers, let's figure out how many numbers from, let's say 1 to 100, right? Natural numbers are divisible by 2 or 3, right? So I want to know if it's divisible by 2 or 3. And this is inclusive, right? So divisible by 2 or 3 or both, right? It could be both. So what's the idea here? Let's let A be the set of all natural numbers from 1 to 100, right? Such that 2 divides n, that'll be our set A. And we'll let B be the set of all, very similar, set of all natural numbers from 1 to 100, such that 3 divides n, right? So A is all the multiples of 2, B is all the multiples of 3. So what we're searching for when we say how many numbers are divisible by 2 or 3, right? What we're really saying is I want to know the size of the union, right? A union B is all the numbers that are from 1 to 100, right? That are divisible by 2 or 3, right? This is how we define a union, right? You take the or of the membership condition for A with the membership condition for B. Okay, so what then can I do? Well, I can think of what's the size of A? What is the size of A? So the size of A is going to be what? The size of this set, 2, 4, 6, and so on up to 100, right? And this isn't too bad to enumerate. You can think of just sort of counting through them. This is 2 is 1, 2, 4 is 2 2s, right? 6 is 3 2s, right? All the way up to 100, which is 50 2s, right? So A has 50 elements in. Maybe not surprising, right? You have the numbers from 1 to 100, half of them are even, half of them are odd, right? So that's the size of A. Now, we also have the size of B. How can I get B? That's all the multiples of 3, right? So I have 3, 6, 9, 12, and so on up to 99 would be the last number before 100 that's divisible by 3. And similarly, I can look at this as multiples, helps me count them, right? So 3 times 1, 3 times 2, 3 times 3, up to 3 times 33. Which 3 times 33 next to a right squiggly brace just looks ridiculous, but that's what it is. So then how many elements is this? There are 33 elements here, right? Because you can just sort of count them off. 1, 2, 3, and so on up to 33, element number 33. So this is A and B. So A is 50, B is 33. But I cannot say that the size of the union is just the sum of the sizes of A and B, right? This is not correct to say. I cannot claim that those are equal. Why? Well, because I claim 83 is too big. That it's too big. Because think about a number like 6, right? 6 got counted twice. I counted 6 as an element of A. I counted 6 again as an element of B. So it's not valid to include that in the count 2 times. It's really just one number that was divisible by 2 or 3 there, right? So numbers like 6 got overcounted. What else got overcounted? 12, right? There's a 12 in here. 12 got overcounted. 18 would get overcounted, and so on, right? So what got overcounted? Well, we need to subtract off what? We need to subtract off the size of A intersect B, which consists of all multiples of 6, right? The intersection of those two sets. Right? If 6 divides in, then it's both in A and B, right? If it's divisible by 6, it's divisible by both 2 and 3 at the same time. So this is what we need to subtract off. So what does this set look like? Well, this is going to look like 1. What? Not 1. 6. There we go. 12, 18, 24, and so on, up to what's the last multiple of 6 before 100 would be 96. Right, and then I can rewrite these again: 6 times 1, 6 times 2, 6 times 3, up until this very last one is going to be 6 times 16. Right? There's our set. And once again, it makes it nice and easy to count when you write it that way. 1, 2, 3, up to 16. So there's 16 elements here. So now I can do principal inclusion exclusion, right? So thus I can say the number of n from 1 to 100 divisible by 2 or 3. That number is what? It's the size of A union B, which by principal inclusion exclusion is size of A plus size of B minus the size of A intersect B, which becomes what? Size of A is 50, size of B is 33. Minus the intersection, right, which is 16. So now I can say, all right, this is what? This is 50 plus 17. This is 67. There we go. There's actually the number. How many numbers between 1 and 100 are divisible by 2 or 3, right? So it's just about 2/3 of them are divisible by 2 and or 3. Right? We always use inclusive or in mathematics, right? So and you can say or, and it's implied that it's inclusive or in the context of mathematics, or you can say and or. Sometimes in English, and or is used for inclusive or, meaning that both is acceptable. So there we go. There's our principle of inclusion exclusion at work, right? And you can sometimes it's helpful to see in a even in a specific case like this, a Venn diagram of what just happened. So here was my universal set, right? I had A, I had B, and I actually need a bigger intersection. There we go. There we go. A, B, right? So A had elements like 2, 4, 8, 10, and so on, right? 8 intersect B, so that's why I purposely skipped 6, 12, right? Had these sort of elements. And then B had elements like 3, not 6, right? The 6 is in the intersection, 9, 12, and so on. Nope, 12 is in the intersection. There we go, 15, right? So there you can see how the elements are distributed, right? So you have in this region, in the circle containing A, you have all the divisors of 2, right? In the circle containing B, all the multiples of 2. In the circle containing B, you have all the multiples of 3, and then in between, you have all the multiples of 6 in A intersect B, right? Out here, you'd have numbers like 1 or 5 or 7, right? You'd have those kind of numbers, which aren't multiples of 2 or 3. Right? So that's how everything worked out. Now, you can also label the size of each of these regions if you want, right? So you could say, hey, I know in here we figured out there were exactly 16 numbers in here, right? So then how many were properly out in this region? Well, there were 50 in all of A, including those 16. So if you wanted, you could say, all right, there's 34 in that region, right? And then how many were in B? How many were properly in B, but not in A, right? This would be 33 minus 16, that's 17, right? Then you could also say how many are out here, right? You could ask that. Well, that's going to be 100 minus the sum of those other 3 numbers, right? Which is, in this case, is 33. So the gray labels, I'm showing how many are in each region, right? And if you want, you can actually even solve the problem this way, and then say that the union is this number plus this number plus this number. That works too, right? So you could also say that the size of A union B equals 34 plus 16 plus 17. If you want to do it without subtraction, you want to do it by just adding each piece, that works great too. More, of course, you still get the same result, right? Far more often, principal inclusion-exclusion is written this way, right? A union B, size of A union B equals size of A plus size of B minus size of A intersect B. But you can do it. So sometimes it's nice to do this sort of Venn diagram approach, right, where you're labeling each region and subtracting out what belongs in some other region as you go. So just kind of showing another way of structuring work like this. So there we go. There's an example where we counted something using principal inclusion-exclusion. Very different from using combinations or permutations or things like that, right? Though the techniques do overlap, certainly. One other thing I want to show is how this looks in a little bit messier case. What if you have 3 sets and you wanted to do inclusion-exclusion? So say you wanted specifically to do the union of 3 sets, right? So let A, B, and C be finite sets, right? Then what happens? You have A union B union C. Well, to figure out what this is, I think the nicest way to do it is actually to think about a Venn diagram, right? So think about our universal set. We have our set A, our set B, and our set C. Right, and I'm going to start by taking, just give me everything in A, give me everything in B, give me everything in C, right? Add them all up. So what do I get when I do that? Well, I'm going to put black dots to show what I just, in what regions just got included, right? So A gives me everything in these 4 regions, right? That's what this term right there gives me in that Venn diagram. B gives me everything in these 4 regions, right? C gives me everything in these 4 regions. So, man, have we overcounted, right? We have some subtracting to do. So anything that's just in A and not in the other two sets, not in B or C, just in B or just in C, right? Without being in A or B, those are fine. Those are counted only once. But anything in any kind of intersection, we've overcounted. So let's start fixing this. So let's subtract off A intersect B. So what does that do? Well, this corresponds to this region, right? So what did I just do there? I am going, what that does for me is it deletes one dot from here and one dot from here, right? That's what I just removed because I subtracted out everything in the intersection. Now, how about B? Let's also subtract off B intersect C. Because what does that do? I get everything in this region is getting subtracted off, right? So I'm going to lose one count from here and one count from here. Then I still have to subtract off the intersection of A with C, right? And when I do that, what happens? Well, it's this region that's got to go, right? So I'm going to lose one dot from each of those. So I get rid of one of these and one of these, right? This is really good because now if you look, this is counted just once, and once. Except what happened? The only thing is now the intersection of all three of them has been completely forgotten, right? We've subtracted, we added it in 3 times, right? We had 1, 2, 3 times that intersection got included, but then it got excluded 1, 2, 3 times. So and this is why it's called inclusion-exclusion, right? That we keep sort of including and then excluding regions until they're all counted just exactly once. So A intersect B intersect C, that's the region that was missing. Well, I put it back. Unfortunately, that didn't break anything else. All that did was add A intersect B intersect C. There we go. There's our principal inclusion-exclusion on 3 sets, right? So this is our next kind of a little messier version of principal inclusion-exclusion. And you can actually do it with as many sets as you want. You can do it with 4 sets, you can do it with n sets, right? So this is, and you always do this, you always get this alternating sum of all the intersections of more and more sets, right? Of how many sets you're taking intersections of. So, all right, great. So there was a little word problem solved using 2-set principal inclusion-exclusion, and then just a demonstration of what does 3-set inclusion-exclusion look like, how to represent it in a Venn diagram, right? So there we go. Thank you.